This video is designed as an overview for sections 8.1 to 8.7 in the textbook. This chapter introduces multiple linear regression with more than one quantitative predictor variable. In this video, we will create a multiple linear regression model by adding in other quantitative variables. We'll interpret slope coefficients for predictors controlling for other predictors in the model. We'll check the validity conditions in multiple linear regression. We'll understand the difference between multiple R-squared and adjusted R-squared. We'll compare models and pick the best one. We'll compute and interpret the variance inflation factor and test and make conclusions about the hypothesis for a variable in the multiple linear regression model. In many studies, it is unlikely that a single predictor is the best model to explain the response variable. Adding in other predictor variables results in a regression model with more than one predictor variable. The estimated regression model will have a slope coefficient for each of the k predictors added to the model. The validity conditions for multiple linear regression are similar to those for simple linear regression. All the variables must be quantitative. We will look at other cases in section 8.9 and 8.11. There must be independence of the responses for each observation. Notice that this assumption is not about the predictor variables. There are three ways we will check the linearity of the relationship. We'll look for a curving relationship in the scatter plot for each explanatory variable versus the response. We'll look for curves in the residual versus fitted plot. And we'll look for clear patterns in the partial residuals on the effects plots. For multicollinearity, we'll check the scatter plot or correlation matrix to assess for large values of correlation between predictor variables and check if the variance inflation factor is larger than 5 for any variable. The equal variance and normality of residuals assumptions are assessed as with simple linear regression. To check for no influential points, use the residuals versus leverage plot looking for values with Cook's distance greater than 0.5. We'll also look for values with leverage greater than the average leverage k plus 1 divided by n. This equation is used to find the variance inflation factor. We can use the code VIF of the linear model in R to find the variance inflation factor for each variable. A VIF with a value over 5 are considered large, indicating high multicollinearity in the model for that particular variable. The square root of the VIF is the number of times larger than the standard error for the slope for variable k is due to collinearity with other variables in the model. When interpreting slope coefficients for predictors in the multilinear regression model, we must first hold the other predictors constant at their mean, then find the simple linear regression model accounting for the other predictors in the model. The slope coefficient is measured as for a 1 unit of our predictor variable increase in the predictor variable, we estimate the mean of the response variable to change by the slope for the predictor variable in units of y, after controlling for all the other variables in the model. When looking at different models, we'll want to choose a specific model because diagnostics are better with one model compared to others. One model explains the responses better than the others. Typically, we'd look at R-squared, but this is only valid for models with the same number of predictors. A priori reasons to use a particular model, for example, a designed experiment, includes variables whose coefficients need to be estimated to find interesting results. And also, model selection criteria suggest one model is better than the others. To choose a model, we will use the adjusted R-squared value. R-squared measures the percent of variation in the response variable explained by the model with the explanatory variable. The adjusted R-squared can be found by using this equation. The adjusted R-squared is not interpreted as the R-squared value and can have values less than 0. We will pick the model that has the largest adjusted R-squared value. Here are some common mistakes when interpreting multiple linear regression models. Don't claim to hold everything constant for a single individual. While this is a mathematically correct interpretation, it rarely can occur in reality. don't interpret the regression results causally. We need to have random assignment in order to say that the change in X causes the change in Y. Be cautious about doing prediction and multiple linear regression. You might be doing extrapolation. Don't think that the sign of a coefficient is special. Adding other variables into the multiple linear regression model can cause a switch in the coefficients or change their magnitude. Multicollinearity in multiple linear regression models. When explanatory variables are not independent of one another, including excluding one variable can impact the other. The t-test for slope coefficients use the estimate divided by its standard error. Assuming the statistic follows a distribution under the null distribution, we can find the p-value. This tests whether each true slope coefficient is 0 or not in a model that contains other variables. We would need to test each estimate individually. The null hypothesis assumes that our slope coefficient is 0, given that the other variables are in the model, while the alternative tests that the true slope coefficient for the predictive variable is not equal to 0, given that the other variables are in the model. Essentially, we're assuming that there's no linear relationship between the explanatory variable k, a certain predictor, and the response variable y in our population, given the other variables are in the model. Our alternative tests that there is a linear relationship between the variables, given the other variables are in the model. The test statistic, which is a t-test, follows a t-distribution with n minus k minus 1 degrees of freedom, where n is our sample size and k is the number of predictors in the model. We can also calculate confidence intervals for the slope coefficient as we did with simple linear regression, using the estimate plus or minus the t-star multiplier with n minus k minus 1 degrees of freedom and the standard error of the estimate. The confidence interval is interpreted as, for a 1 unit of predictor increase in the predictor, we are 95% confident that the true mean of the response changes by between the lower limit and upper limit units of y in the population after adjusting for the other x variables. And it is important that we list those in our interpretation. In the multiple linear regression summary, there's an f-test and p-value reported at the bottom of the output. This test is called the overall f-test in multiple linear regression. It tests whether any of the slope coefficients should be included in the model. The null assumes that no explanatory variables should be included in the model, while our alternative tests that at least one explanatory variable should be included in the model. The f-test statistic uses this equation to calculate, and it follows an f distribution with k numerator and n minus k minus 1 denominator degrees of freedom. Next, we will work through an example of the SNOWTEL data using the data set with the 2 observations removed as discussed in the textbook. We want to see the impact the variables elevation, max temperature, minimum temperature have on the snow depth. We can see the values of correlation between each pair and the corresponding scatter plot on the scatter plot matrix given here. We can see that all of the variables have a moderate to strong relationship with the response, snow depth. Elevation has the largest correlation coefficient for our relationship between the predictors and the response variable. We can also see that we have strong correlation between minimum temperature and elevation and maximum temperature and elevation. We're going to fit the multiple linear regression model with all 3 predictors. So k is equal to 3. So here's our linear model output showing our y variable and showing our different x variables. Here are the estimates for our linear regression model, giving us the linear model where we're looking at the predicted snow depth is equal to our y-intercept negative 213.3 plus the slope coefficient 0.0269 times the elevation plus 0.984 times the minimum temperature plus 1.243 times the maximum temperature. Let's check the validity conditions for this model. For the quantitative variable conditions, all three predictor variables, elevation, minimum temp, maximum temp, are all quantitative, as is the response variable, so that validity condition is met. The observations are based on a random sample of sites from the population, and the sites are spread around the mountains in Montana. So it would be reasonable to assume that the sites are independent of one another. You could read in the textbook on page 310 about more information about the independence of these observations. To check for linearity of relationship, we'll first look at those scatter plots. Looking at each of these scatter plots, where we're looking at the predictor and the specific response snow depth, we can see that we don't have much evidence against linearity. They don't show any clear nonlinearity. Next, we can look at the diagnostic plots for the multiple linear regression model. In the residuals versus fitted plot, again, we have a nice straight line here showing no evidence of a curve. So we have little evidence against linearity. And we can also look at the partial residuals in the effects plots. Again, we're not seeing much evidence against linearity based on these plots, as there are no patterns in the partial residuals. Next, let's check for multicollinearity. If we go back up to our scatter plot matrix, we can definitely see some evidence of multicollinearity, as we see a correlation of negative 0.91 between elevation and min temp, and we can also see a correlation of 0.77 between min temp and max temp. We'll also look at the variance inflation factor. Here we see the variance inflation factors for each of our variables. So we can see that two of them, elevation and min temp, are greater than 5. So it looks like we do have some evidence against multicollinearity in this example. Next, we'll look at equal or constant variance in our diagnostic plots. While there might be a little more variability in the middle of the fitted values, this is more of an artifact of having a smaller data set when we look at our residuals versus fitted plot. So there's not evidence against constant variance. It appears that the values follow the one-to-one line pretty well in our normal QQ plot, so we have little to no evidence against normality. And next we'll check for influential points. We do not have evidence against no influential points, as there are no values with a Cook's distance greater than 0.5. As far as values with high leverage, we would take 4k plus 1 divided by our observations of 23, which is 0.17. So it does appear that some of our values have a leverage above 0.17. Next, we will interpret the slope coefficient for elevation while holding the min temp and the max temp constant at their mean value. To find the means for min temp and max temp, we use this code right here, and we find that the average min temp was 27.82609 degrees Fahrenheit, and the average max temp was 36.3913 degrees Fahrenheit. So to find the simple linear regression model for elevation while holding min temp and max temp held constant at their averages, we would plug in the values for the mean temperatures into our equation to find our new y-intercept value. So this gives us a new line of regression showing the estimated snow depth is equal to the y-intercept of negative 140.69 plus the slope coefficient of 0.0269 times elevation. When we interpret this slope coefficient, we would say for a 1 foot increase in elevation, the expected average snow depth increases by 0.0269 inches after controlling for min temp and max temp in the model. We can also predict the mean snow depth for an elevation of 5,000, assuming min temp and max temp are included in the model. So here we've plugged in the value of 5,000 for our x value and find a mean snow depth of negative 6.19. For an elevation of 5,000 feet at the average min and max temperatures, we expect a mean snow depth of negative 6.19 inches. We will pick the model that has the smallest adjusted R-squared to assess further. Looking at the adjusted R-squared values for each model given here, we would choose the model with elevation plus max temperature as predictors, as that has the largest R-squared adjusted value of 0.8344. We will proceed with this new model, looking at snow depth with predictors of elevation and max temperature, to work through a hypothesis test. Here are our estimates showing the intercept of negative 167.5, the elevation slope coefficient of 0.0241, and a max temperature slope coefficient of 1.253. The null hypothesis for this test assumes that there is no linear relationship between max temperature and snow depth in the population given elevation is in the model. So we're going to test that the true slope of max temperature is equal to 0 given elevation is in the model. The alternative tests that there is a linear relationship between max temperature and snow depth in the population given elevation is in the model. So we're testing our max temperature, so we're looking at a t value using our estimate of 1.253 divided by our standard error of 0.5385, and that gives us a t value of 2.327 and a p-value of 0.031. This shows that there is strong evidence against the null hypothesis that there is no linear relationship between max temperature and snow depth in the population, given elevation is in the model. This is based on a t-distribution with 20 degrees of freedom and a test statistic of 2.327, a p-value equal to 0.031. So we can conclude that there is a linear relationship between max temperature and snow depth in the population, given elevation is in the model. We could also test that there is a linear relationship between elevation and snow depth in the population, given elevation is in the model, and look at this test statistic here and the p-value for that test statistic. To find the confidence interval, we can use R as a calculator and put in our slope coefficient plus or minus the t-star multiplier times the standard error. And this would give us a confidence interval of 0.1297 to 2.376. Or we could also use this code confident for our model, and that shows us our 95% confidence interval for our slope coefficient for max temp. And we can also see the 95% confidence interval for the slope coefficient for elevation. To interpret the confidence interval, we'd say for a 1 degree increase in maximum temperature, we are 95% confident the true mean snow depth increases by between 0.130 and 2.380 inches after accounting for the elevation of the sites, because we do need to account for the other predictor being in the model. For this multiple linear regression model with elevation and max temp as predictors, the F statistic is given in our output of 56.43 using 2 and 20 degrees of freedom and a p-value less than 0.0001. This shows that there's very strong evidence against the null hypothesis that the true slopes for the two predictors, max temperature and elevation, are 0. This is based on our F statistic of 56.43 using an F distribution under the null with 2 and 20 degrees of freedom and a p-value less than 0.0001. We would conclude that at least one of the two slope coefficients is different from 0 in the population of snow-tilled sites in Montana. This video is an overview showing multiple linear regression models with all quantitative predictors. In section 8.9, we will look at adding in categorical predictors to the multiple linear regression model.